Jai Hind, myself Nehakar. I am assistant professor in Ajay Kumar Garg Engineering College. And today's lecture is on the topic bipolar junction transistor in common character configuration. This topic has been taken from the subject Fundamentals of Electronics Engineering. So, basically transistor. Transistor is a three-terminal device. It consists of emitter, base and collector. So, emitter is a terminal which provides the charge carriers, and collector is a terminal that collects the charge carriers that is coming from the emitter. Base controls the flow in between the emitter and the collector. Like if we have a PNP transistor, means like this is P and P. So, this P is our emitter, this N is our base, and this P is our collector. So, when we construct, if we connect two diodes back to back, like we have this P and N, this is our diode, and another diode is N and P, and we connect these two diodes, to then it will not make a transistor, because in this transistor the construction is different. Like emitter construction is different, collector construction is different, and base construction is different. The emitter is highly doped. This is heavily doped. Because it provides a charge carriers, that's why it is heavily doped, and the size of the collector is very large, because it collects the charge carriers that is coming from the emitter. That's why while constructing the transistor, emitter size is different, collector size is different, base size is different. Collector size is more and emitter size is least. Emitter size is less than the collector size. And also, like here the PNP transistor is in this way, and like NPN transistor will in this way. This N will be the emitter, P will be the base, and this N will be the collector. Similarly here, the doping level of the emitter will be high and the size of the collector will be high in all these cases. Like according to doping will be high for emitter, and then for collector, and then for base. And for size wise, the collector size will be highest, then emitter, and then base. So, this is the doping and the size profile of a transistor. The main function of the transistors are amplification. It acts as an amplifier in common emitter configuration, and also it acts as a switch. It acts as a switch in two modes like cutoff and saturation. When it works in cutoff and saturation mode, then it will work as a switch. And when it is working in an active mode, then it will work as an amplifier. And generally, common emitter configuration is used for the amplification purpose. And the symbol of the transistor is like this is our collector, this is emitter, and this is base. And we have to make the NPN transistor. Means like N is our emitter, P is our base, and N is our collector. So here arrow will be in this direction. P is our base, so arrow will be in this direction. This is NPN transistor. And like if we have like in this way, this is our transistor, this is emitter, this is base, and this is collector. Sorry, this is base and this is collector. Now we have to make the PNP transistor. So P is our emitter, N is our base, and P is our collector. So this arrow will be in this direction. Always there will be arrow on the emitter side. It will not be on the collector side. And also this BJT stands for bipolar junction transistor. Means bipolar means here both type of charge carriers will involve in the conduction. Like electrons and holes, both will be involving in the conduction. And it is also called as a BJT is also called as a current controlled current device. It is also called as a current controlled current device. Current controlled current device means here the output current in the BJT is controlled by the input current. Like in case of the common base configuration, IC is the output current and IE is the input current. So this output current is controlled by the IE. That's why it is called as a current controlled current device. Like in case of the common emitter configuration, IC is the output current and it is controlled by the base current, by the amplification factor beta. So this is why this BJT is called as a current controlled current device, because the output current is controlled by the input current. So here the construction profile of the transistor includes the Emitter. The emitter, I have already told that emitter, the doping level of the emitter is very high. The portion on one side of the transistor that supplies charge carriers, electrons or holes, or to the other two portions. The emitter is heavily doped region. Emitter of a PNP transistor supplies host charges to its junction with the base. Similarly, the emitter of a NPN transistor supplies free electrons to its junction with the base. After that, collector is there. So collector is the third part, that is, I have told you, like, this is our emitter, this is base, and this is collector. So collector basically collects the charge carrier that is coming from the emitter. And the base is the middle portion which forms two PN junction between the emitter and the collector, and is called the base. The base of the transistor is thin as compared to the emitter and is a lightly doped portion. The doping level of the base is very less, and also its size is also very low, because generally what happens, this is like emitter, base and collector. So emitter is input circuit, it is forward bias like P and P, and this circuit is always reverse bias. And if both, this is input circuit, like when will be transistor in cutoff, when we connect the input circuit in reverse bias and output circuit also in reverse bias, both are in reverse bias. Like P will be connected with the negative supply and this N will be connected with the positive supply. So this input circuit will also be in reverse bias condition, and output circuit, that is BC, is also a reverse bias condition. And this connection is the common base connection. Means base is in the input circuit also, base is in the output circuit also. So that's why it is called this configuration. The circuit that I have drawn on this circuit was the common base configuration circuit. Like forward active means, like if we have made this NPN transistor, this NP is in forward bias and this is in reverse bias. So this is called as a forward active mode. In cutoff, both these two junctions are in reverse bias. In saturation mode, both these are in forward bias. If this is in reverse bias, for input junction will be in reverse bias, then no charge carriers will be moved to the input side, output side. That's why in cutoff mode, no current will be flowing. So here we can see, this is how our transistor works. So we can see we have connected the P and N terminal. So P terminal is connected with the positive supply, N terminal is connected with the negative supply. So this part is acting as a forward bias PN junction diode. So here, due to here, in forward bias PN junction diode, majority charge carriers will flow. So here holes will be flowing in this direction. Now the output circuit, that is the NP circuit, is in reverse bias. In reverse bias configuration, always minority charge carriers will be flowing. This is a reverse bias PN junction diode. So here in reverse bias, minority charge carriers in N-type material is holes. So here holes are moving from this side. So this is when we combine these two diodes, it will form a PNP transistor. So here in PNP transistor, this part is forward bias and this part is reverse bias, as indicated in this figure. So when we combine these two, we can see here final current will be due to the majority charge carrier that is coming from this emitter side, and also due to this minority charge carriers. So this minority charge carriers is indicated by the ICO, and this majority charge carriers is indicated by alpha I. Alpha is means like when majority charge carriers comes from emitter to base, some of the majority charge carriers will be combined with the electrons present in this base and they will form the base current, and rest of the holes they will come collected within the collector side. So all of the charge carriers that is coming from the emitter terminal, they are not able to collect in the collector. Some of them get recombined with the charge carriers present in the base and they form the base current. Rest of the charge carriers, they come in the collector. Like here electrons started, these electrons, some of the electrons will get recombined here and they will form the base current. Here base current will be there due to the combination of electrons and holes. And now rest of the majority charge carriers will be collecting in the collector. So in collector current, this IC would be equal to alpha I plus ICO. This ICO is the minority current. This minority current is flowing because this circuit is in reverse bias. This NP is reverse bias PN junction diode, due to which minority current is flowing. And this alpha, this is the amplification factor. This is amplification factor, and its value is given as 0.95 to 0.99. And we can see here the output current IC is alpha times of IE. So if IE, this is 0.9 and this IE is 10, so it will be 9. So we can see here output current is less than the input current. Input current is our 10 and output current was 9. So it means here current gain will not be there in the common base configuration. So here we can see this IE is equal to IE means this current, the current that is coming from the emitter junction. It is equal to the base current and then the collector current. And this IC here, this IC is equal to the IC majority plus reverse bias current. This ICO minority, this is also called as a reverse saturation current or leakage current. So here this is a common base configuration. We can understand the working of the transistor in 3 modes, that is a common base configuration, common emitter configuration and common collector configuration. Common emitter configuration is generally used as an amplifier, and common collector configuration is also called as the emitter follower. Emitter follower is the common collector configuration. So here this is a common base configuration. So I have already told you that this is our PNP transistor, this is emitter, base and this is collector. So this circuit, input circuit is always in forward bias. So here emitter and base is the input circuit, that is in forward bias, and base and collector circuit is in reverse bias. So here this is a reverse bias is here. So that we have understood that holes will come from this place to this place, and some of them they can recombine, and rest of the holes will be collected in the collector region. So here this is the input characteristics of the common base configuration. So for drawing the input circuit, we have to see the input part. Like this is the input part. This is the input part. Here input side we can see emitter and base. So emitter is at the input terminal. So IE is our input current. So at input circuit, what we will see, the input current is IE, and the voltage is applied in between the base and emitter. So this will be plotted in between IE and VBE, keeping constant at constant output circuit voltage. So output circuit voltage is this, that is VBC. Output circuit voltage is applied in between the base and collector, that's why it is the VBC, and input circuit is that is a VBE. So this is input characteristics is plotted in between the IE and VBE, and this IE and VBE, this is plotted in a manner so that the PN junction diode is in a forward bias, because in forward bias the characteristics is like in this way. So this is VBE and this is IE, and this is plotted at constant VCB. So this was the input characteristics curve. And here we can see this is the output characteristics curve. So output characteristics, this is the output circuit and this is the input circuit. Output circuit, we can see the output current is IC. So it will be plotted in between IC, and the output circuit voltage is the VCB, IC and VCB, keeping IE as constant, keeping IE constant. So here we can see this characteristic was in this way, like in this way. So this was plotted different IE, and this was IC and this was VCB. So this region was active region, this was cutoff region, and this was saturation region in the output characteristics curve. Active region, cutoff region is this region, because here the current flow is 0. In cutoff region occurs when the input circuit is also reverse bias. So if input circuit will be in reverse bias, in that case majority current will be 0. It will be very less amount of current that will be collected in the collector side. So alpha, this alpha is the amplification factor, and this is given by the, like the circuit was in this way, PNP, and this is forward bias, this is reverse bias. So this is the input current, this is the output current, and this is the output current. So the ratio of output current upon input current is called as the amplification factor, that is given by alpha DC. And when it is operated in the AC mode, and it is given by the delta IC upon delta I and keeping your VCB constant. The value of alpha is lying in between the 0.9 to 0.998. It means current amplification is not achieved in case of common base mode. Here the voltage gain is high, but not current gain is not high. So common base is generally used in the high frequency applications. And here we can see this is the common collector configuration. Common collector configuration is also called as the emitter follower. It is also called as the emitter follower because here output voltage is always equal to VIN minus VBE, and V0 is the value of VBE is 0.7. So if VIN is 10 minus 0.7, it is equal to 9.3. So V0 is 9.3 and VIN is 10. So we can see output and input is almost equal in case of the common collector configuration. So so we can see output is following the input, and output is always taken in case of common collector configuration. We can see the output current is the emitter current. So here the output is taken across the emitter. That's why the emitter voltage is always follows the input voltage. Emitter voltage is this. VE is the output voltage is the emitter voltage, and this is very much equal to the input voltage. That's why it is called as the emitter follower. Means emitter is following the input voltage. So here we can see common collector configuration. This is the PNP. This is our emitter. This is base, and this is collector. Now the collector will be in input side as well as in output side. So here input circuit is always forward bias. So base and its collector, they form the input circuit. So they will be connected in forward bias. So this N will be connected with the negative supply and this P will be connected with the positive supply. And we will connect the reverse bias circuit in reverse bias, output circuit in reverse bias. So output circuit will include the collector and the emitter. Now we can see emitter is also P and collector is also P type. So in which who will be the reverse bias? So in that case, collector will always win in reverse bias. So this collector will be connected with the negative supply and emitter will be connected with the positive supply. So similarly here we have taken the NPN transistor and this N is the collector. So it will be in the input circuit as well as on the output circuit. So input circuit, we can see the base and collector are the input circuit and they are in the forward bias. P is connected with the positive supply, N is connected with the negative supply, and the output circuit, that is the collector and emitter, they will be in the reverse bias. Now we can see both are N type. So who will be connected with the negative supply? In that case, collector is always in reverse bias. So collector will be connected with the positive supply and emitter will be connected with the negative supply. So in this way, collector are reverse bias in both cases. And here we can see the input characteristic will be plotted in between the input current is our IB and it will be plotted in between the VBC at keeping constant. What is constant? It will, in that case, VCE is constant. This is the input characteristic that will be plotted. And output characteristics, we can see they will be plotted in between IE versus VCE. At what constant? We will be keeping IB is constant here. So this is for the output characteristics and this is for the input characteristics. And direction of current we can see here. We can see the emitter. Emitter we can see this is here N type. So direction of current is always from P to N. So direction of current will be in this way. This is the emitter current moving upward. And IE is the sum of IB plus IC. So collector current will be moving upward and base current will be moving this side. Here we can see, always see the emitter first. So we can see the emitter is P type. So direction of current is always from P to N. So it will be flowing from this side. So this will be the emitter current. Now collector current will be downward and base current will be here because IE is the sum of IB plus IC. So IE will be distributed in IB and IC here. So these are the characteristics of input and output characteristics of the common collector configuration, that is also a emitter follower. So here we can see this characteristics very much similar to the common emitter configuration. This is the active region, this is the cutoff region, this is the saturation region. So everything is almost same here. But in case of input characteristic, we know from the circuit that we have drawn, that like circuit was in this way. This was the collector, this was the emitter, and this was the base and emitter, like N, P, N. So this was forward bias and this was reverse bias in this way. So this is the VCE. So we can see from this diagram, this VCE is the voltage applied across this. This is equal to VBE plus VBC. So we can see VBE is equal to VCE minus VBC. So here if we keep this voltage VCE constant and we increase this VBC, then VBE will automatically decrease. If we keep VCE constant, this is constant, and VBC is continuously increasing. So we can see VBE will decrease, and VBE will decrease, it means IB will automatically decrease. So this plot is between input characteristics is plotted between the VCB and IB. And here we can see if we increase the VCB, this IB current is continuously decreasing. Here I am saying the same thing. We are increasing the VBC, VB is decreasing, so IB will decrease because IB depends upon the VBE. So IB will decrease. So this this graph is plotted by assuming this characteristic. If we increase the VCB, then IB current will decrease. So common collector configuration is basically used for the impedance matching. The application of this configuration is impedance matching. Impedance matching, because it has a high input impedance and low output impedance. So this characteristic is basically used for the impedance matching. So these are the differences between the BJT and FET. The next topic will be the FET. So BJT is the bipolar junction transistor and FET is a unipolar junction transistor, unipolar transistors. Bipolar means both type of charge carriers will be involved in the conduction, means it will include the electrons as well as the holes. And FET includes only one type of charge carriers, either it will be electron or it will be holes. BJT is a current control device, current device. I have told in earlier slide, IC is equal to beta IB. FETs are the voltage controlled current dips. Here the current is the ID, that is the drain current. This current is controlled by the VGS voltage, gate source voltage. So that's why it is called as, FET is called as a voltage controlled current device. The input circuit of the BJT is forward bias and therefore BJT has a low input impedance. We have seen this already. The input circuit of the FET is reverse biased and therefore FET exhibits relatively higher impedances. The base current controls the output current. BJT has more noisy operation because it consists of junctions, input common emitter base junction, base collector junction. So different junctions are there, input junctions, output junctions. So that's why it is somewhat noisy in nature. FET is less noisy compared to the BJT. FETs are relatively smaller in size, especially in case of the integrated circuits composed of many transistors. FETs are most preferred during the applications of high current. So these are the differences in between the BJT and FET. Now different types of FET. So basically the FET is of two types, junction field effect transistor, and this is a MOSFET, that is the metal oxide semiconductor field effect transistor. JFET works only in the depletion mode, and that is and it is of two types, N channel and P channel. Metal oxide transistors are of two types, depletion and enhancement. It can work in both modes, like depletion D MOSFET works only in both modes, depletion mode and enhancement mode. and means it is again divided into D MOSFET and enhancement MOSFET. Enhancement MOSFET only works in the enhancement mode. It works in both mode, the depletion mode and enhancement mode. And again, all the depletion mode, enhancement mode, they are all in the N channel and P channel. So here the operation of the JFET, how will this JFET is in working condition. So here we have taken the N channel JFET. So for N channel JFET, we will take a slab of N type semiconductor. It will act as a N channel, and then we will we have this is N channel, and we will put some blocks of P type semiconductor here. So they will act as a gate. Now we will internally connect these gates like in this way. So this is our gate. Now we will put a metal contacts here. So this will act as a drain. This will act as a source. Now we have to connect the drain and source. So source, like we have seen in the BJT, emitter act as it provides a charge carrier. Similarly here, this source will provide the charge carriers, and drain will collect. The drain is similar to the collector, like in BJT. So it will collect the charge carriers that is coming from the source. So source, drain in source, drain will be connected with the positive supply and source will be connected with the negative supply. So this source will provide the charge carriers, that is the electrons here. So these electrons will move upward. When we connected source, if this is N channel, source will be connected with the negative supply. If the P channel, source will be connected with the positive supply. Because source, we have to give the repulsive force to the source, so that it may release the charge carrier. So electrons will be repelled from this source to the drain, and current will flow obviously in opposite direction. So this is the analysis when VGS is 0. First analysis is then when VGS is kept at 0. Gate and source are short circuited and VD supply is applied in between the drain and source. Now if we increase this drain and source supply, we can see the reverse bias across the drain side will be more, because drain is N type and it is connected with the positive supply. Source is N type and it is connected with the negative supply. So reverse bias is across the drain, not at the source. So if we increase the VDS, the reverse bias across the drain side, it will increase. So we can see the depletion region that will be in between the P and N type. This depletion region will be increasing, but it will increase more at the drain side in comparison to the source. So this depletion region will become like in this way. It will be more at the top and narrow at the bottom. So if we increase the VDS voltage, a point will come when both the depletion region will touch each other. So at that point, when they are touching each other, a constant amount of current will be flowing. This current will not be going to 0, but a constant amount of current will be flowing, and that in that case, that condition is called as a pinch-off condition. And that current at VGS 0 is called as the IDSS current, means drain to source current when gate and source is short circuited. So this graph will be like in this way, like this is the VDS and this is the ID. We are continuously increasing the VDS. So this graph will be in this way. So this will be the this current is called as the IDSS, and this is the VGS at 0. Now we can change the supply across the gate and source. We can connect in the reverse bias. So for reverse bias, this P will be connected with the negative supply minus, and this will be connected with the positive supply. Like this VGS is -1 volt. So we have to do the analysis of the JFET in two ways. First is the VGS 0, and another analysis will be done when the gate and source is in reverse bias. Means it will be connected with a negative supply, that is -1 volt. -1 volt will be applied for the N channel, and if it is P channel, it will be connected with the positive 1 volt. So now if we connect the reverse bias at this side also, and in this, so we can see reverse bias is here also, reverse bias is here. We have applied the VDS in the same way, like in VGS 0. So reverse bias is coming from this side also, reverse bias coming is this side also. So pinch-off condition will come early. So at VGS 0, VGS minus 1 volt, it will be like in this way. Like this was the pinch off voltage Vp, and now it has become like in this way. And also if we increase further, it will become Vgs is equal to minus 2 volt. It is Vgs is equal to minus 3 volt, and this is the Vgs is equal to Vp. So this will be this is the drain characteristic curve. Drain characteristic curve of JVT in N channel, and it also follows the Shockley equation. Like Shockley equation is this: ID is equal to IDSS 1 minus VGS upon Vp ka whole square. So in Shockley equation, if we put VGS is equal to Vp, we can find that ID barabar IDSS. And if VGS is equal to 0, then if ID is equal to 0, if VGS is equal to Vp, then it will be equal to ID will be equal to 0. And if ID is equal to 0, then VGS is equal to Vp. So these two things will be there. Miss Shockley equation is like ID is equal to IDSS 1 minus VGS upon Vp whole square. If we put VGS is equal to Vp in this equation, then ID will be equal to 0. And if we put ID is equal to 0, then VGS would be equal to Vp. So from this we can plot this graph. So we can see here VGS Vp. So both these things are same. But we can see if we put a VGS is equal to Vp, then current will be 0. And if we put here VGS is equal to 0, then it will be equal to ID is equal to IDSS. If we put VGS is equal to 0 here, then ID will be equal to IDSS. So because this axis is VGS and this axis is ID, so here VGS is 0, this will be equal to IDSS, and here ID is equal to, that is VGS barabar Vp. So this is the transfer characteristics curve that we have plotted. So we can see similarly we can plot this for the P channel also.